In this section, we are exploring the inverse of a matrix. Now, here we're going to begin by investigating a matrix that's analogous to the algebraic reciprocal of a non-zero number, also known as the multiplicative inverse of a non-zero number. So that's where I'd like to begin. Let's start with a quick review of algebra. So in this quick algebra review, we are looking at the multiplicative inverse of a non-zero number. So let's go ahead and let x be some non-zero number. Any non-zero number your little heart desires. So then the multiplicative inverse, or that algebraic reciprocal, tells us that this non-zero number x multiplied by x to the minus 1 equals 1. And it also tells us that x to the negative 1 multiplied by x is also equal to 1. So that's the multiplicative inverse. And we now want to take this and generalize it to the inverse of a matrix. Now, the matrix generalization of this multiplicative inverse has some conditions that we need to keep in mind. The first condition is that it requires both of these equations to hold true. So it requires both of the equations above to hold true. And why, you might be asking? Well, we need both equations to hold true because we know matrix multiplication is not commutative. Or not in general commutative. So we need both of those equations above in terms of matrices to hold true. So in other words, if we have some matrix A, so we need matrix A multiplied by the inverse of matrix A to be equal to the identity matrix. And we also need that the inverse of matrix A multiplied by matrix A is also equal to the identity matrix. This is that special case for matrix multiplication. Now, the second thing that we want to keep in mind as we explore this generalization is that there's no slant notation for division. So absolutely no slant notation for division. Now, what does this mean? This means that the inverse of matrix A cannot be written as 1 by A. These are totally different concepts, right? This negative 1 is simply notation for the inverse. It is not an exponent. So there is no slant notation for division. Now, the last condition I want you to make note of is that both of these matrices, matrix A and the inverse of matrix A, must be square. So both matrices, matrix A and the inverse of matrix A, must be square. So the number of rows must be equal to the number of columns for a matrix to be invertible. Now, with this last condition here, saying that both of these matrices must be square, we need to consider the following note. Now, one could say that an M by N matrix A is invertible if there exists N by M matrices C and D, such that the product of matrix C times matrix A is equal to the N by N identity matrix, and that matrix D times matrix A is equal to the M by M identity matrix. But these implications imply that matrix A is square, and that matrix C is equal to matrix D. So thus, A is invertible and defined if both matrices are square. So let's go ahead now and look at an informal definition generalizing what we have here. So here we go. We want to summarize the matrix generalization for an inverse. So we say that in n by n matrix A is said to be invertible if there exists an n by n matrix defined as matrix A to the minus 1 such that the product of matrix A and the inverse of matrix A is equal to the n by n identity matrix, and that the product of the inverse of matrix A with matrix A is also equal to the n by n identity matrix. So if both of these equations are holding true, then we say that matrix A is invertible. So again, a matrix that has an inverse is called an invertible matrix. It's also sometimes called a non-singular matrix. Now, when we say that a matrix has an inverse, or it is invertible, or if a matrix is non-singular, this is letting us know that the matrix equation involving that matrix A has one unique solution. Now, a matrix that does not have an inverse is called a non-invertible matrix. Or it is sometimes also called a singular matrix. So if a matrix does not have an inverse, or if a matrix is non-invertible, or if a matrix is singular, then we say that the matrix equation involving this matrix A has infinitely many possible solutions. And we're going to be exploring both of these statements in much more detail very shortly. But first, we need to go through and establish a more formal definition for the inverse of a 2 by 2 matrix and how to go about finding such an inverse.